All right, so great. I would like to visit with you for a little bit now on a topic that I've been working on for the past three some odd decades, I guess, space debris, which is, of course, related to space programs, astronauts, space safety. Perhaps you've heard the phrase space situational awareness being talked about. This is kind of related to that. Space situational awareness, space traffic management has more to do with actual knowing where the stuff is in space, whereas what I've been working on is what happens when a spacecraft interacts with that stuff. Okay, so anyway, basically then I will start the process going. Good. Hopefully you can see a new slide. If something is wrong, please let me know. I tend to look at things kind of simply, I guess. You know, there's all this stuff in Earth orbit. Some of it's useful and some of it's not so useful. And so I thought we would start by talking about very briefly some of the useful stuff like satellites, and then move to some of the not so useful stuff like orbital debris. So I'm a professor, as was mentioned, and I probably speaking with a whole bunch of students out there. And so being a professor, you being students, I have to give you a quiz, right? Okay, so here is a pop quiz for you. Ready? You don't have to write the answer down. Just think of it in your head. You know, that's okay. What was the first Earth orbiting satellite? Okay, you got that figured out? What was the first Earth orbiting satellite? Okay, everybody who said the moon, come to the front of the class. And no, just kidding. This was a trick question. Sorry, I know. I should have said human-made Earth orbiting satellite, because then probably we would have seen everybody say Sputnik, and that's true. But of course, the moon has been around for a few more years than Sputnik. But anyway, the Russians launched Sputnik. We, the United States, came along a little later with our Explorer satellite. And since then, since 1957, through the 60s, the 70s, the 80s, the 90s, and I don't think anybody out there's probably been born yet, but you know, a country every now and again, every few years, a new country joined the space club. And this is not just launching a satellite, but this is launching a satellite with your own rocket. And you'll see here on the bottom is New Zealand, yay! And you'll see here Australia, yay! Even though the UK got the credit because the UK built the satellite and built the rocket, it was launched in Australia. So yay. And now you have a space agency in Australia for a few years now, which I think is fabulous. And you guys are doing great work in the space situational awareness area. So I think it's just wonderful. But you know, every few years there used to be quite a bit, and then recently there were a lot more launches. This sketch is a few years old, but it kind of gives you the idea that for a long time the United States and the Soviet Union were the primary launchers. Of course, we kind of calmed down in the 70s and 80s in the US. We had our economic recession here and never really caught up. Russians just kept going great guns. But I think the reality of the world hit them here around in the 90s, 2000. China came on strong here and is launching quite a bit. And here we have other countries, European Space Agency, India, Japan, and some other recent countries are coming into the fore now. And this was primarily, we launched our satellites into two distinct regions of space: low Earth orbit and geosynchronous orbit, LEO and GEO. There's a couple of satellites here and there in MEO and in the highly elliptical orbit, but for the most part, you have a lot of stuff near Earth and you have a lot of stuff far away from Earth. What do all these satellites do? Well, if you take a look at these, what do we got here? We got the blue, the yellow, and the pale blue-green here. These are all communication. This is almost 2/3 of the satellites that are up there have to do with communication. What that means is that most of the satellites that are up there now are there so that you can order pizza for lunch, or whatever it is that you would like to have for lunch, or talk to your friend, or figure out where you're going to go after work. That's what most of the satellites do. Yes, some of them are technology oriented and science oriented, and yes, there is some military stuff going on in some weather satellites, but for the most part, it's all about communications, different kinds of communications. And this was fine, good and dandy, and every few years, some more satellites went up in space until about 10 years ago, when along came. Now, if you know who these people are, then you're probably as old as I am, or you used to listen to the same music your parents used to listen to. These are the new kids on the block, but no, never mind. We're not talking about these new kids on the block. We're talking about these new kids on the block. Starting about 10 years ago, lots of different companies came up with these great ideas to launch 10, 20, 30, thousands of satellites into low to medium Earth orbit. SpaceX, of course, is the one that is gathering a lot of noise right now. It's launching many satellites every few weeks, but even Amazon has gotten into the deal now, into the fray. So I mean, these numbers should be like an odometer on your car. I mean, they should just be changing, because there are so many new satellites, and the estimates of 25,000 to 45,000 new satellites in the next 5 to 10 years seem old now. I saw a number of 65,000. I just don't know, but there's just all these plans that many satellite owners are wanting to join the space club. Now, I mean, there's good news to all these satellites. I mean, going up there, yeah, they are going to serve a useful purpose. They're going to bring communications to places where internet is slow or non-existent. The World Wide Web is going to explode in terms of speed and reach. There'll be better help with disaster management, because you need many different kinds of satellites with many different kinds of optics to deal with the many different kinds of natural disasters and man-made disasters, human-made disasters that can happen as well. But the reality is, for those of us who work in the space debris business, we're sitting there watching this going, oh my gosh, what are they doing? There is going to be a huge increase in the number of space objects and the population, that, never mind the possibility of impact by a piece of junk because two satellites collided when they weren't supposed to. But for those of us who worry about close approach warnings, right now, it's not unusual for a company to be told by NORAD that, hey, you're going to come this far away from a satellite, and you should, decide what you want to do. Do you want to get out of the way, or do you want to just let things ride and hope that our numbers are wrong and that you guys are going to miss each other? It's up to you guys to figure it out. And so these two satellite companies then go and do whatever they feel is appropriate. Well, instead of happening once or twice a day, this is likely going to happen maybe 5 times an hour now, or 10 times an hour. And if you do the math, that's every 5 to 10 minutes. That's just mind-boggling how we are going to have to keep track of all this stuff. So, and of course, hey, if you are an astrophotographer, I'm sure you can appreciate how this photo of Comet Neowise, this was last summer in the northern hemisphere. I apologize, I'm not sure if it was visible in the southern hemisphere, but in the northern hemisphere, we had this wonderful comet apparition. And hey, this photo kind of shows you one of the problems. These are all Starlink satellite trails. Kind of ruins a night's work sometimes. So reality is, it's going to be a problem. And now, this I think was just in Wired like 2 days ago. So if you look up SpaceX Wired light pollution, you'll see an article that people have been talking. People are finally starting to realize that, hey, there's a lot of stuff going up that's really bright, and it's going to ruin things for a lot of people doing science up there. What can we do about it? Well, this is not news to those of us who have been saying this for the past 5 years or so, but it takes time for the rest of the world to catch up sometimes, and I'm just glad that they are. So that's the useful stuff. So now let's turn our attention to the fun stuff, which is the not so useful stuff. That's the orbital debris. All right. And so for the next little bit of time, I'm hoping to answer some questions that might occur to anybody who's starting out in any kind of remediation effort or any kind of environmental effort, if you will. Where does this stuff come from? How much of this stuff is out there? What happens if I interact with this stuff? Can I protect myself against this stuff? Can I clean up this stuff? And if I do nothing, is the situation going to get better or worse? So these are kind of questions that's specific for orbital debris, but as you can imagine, they're applicable to just about any kind of environmental concern or any kind of environmental problem. I'm a big movie buff. I love movies. And if you went out a few years ago and saw this movie, Gravity. Okay, yeah, I know. Fast and loose with the physics. I know. I get it. Sandra Bullock's hair shouldn't look that good in real life. I know. But the great part about this movie, I thought, was how it all started. And yeah, timelines are timelines. And sure, this stuff can take decades or years, and we have to tell the story in under 90 minutes. So let's move up the timeline a little bit. But the idea of space debris creating this runaway cataclysmic event is not that far from reality. It's possible. And the fact that this movie introduced millions of people around the world to this possibility, I thought was great, because it's just really cool to see what you work on being brought to an audience in such a, I thought it was clever. I can check my reality checker at the door. I don't mind. I enjoyed the movie. I thought it was great. So where does all this stuff come from? First question. Well, the stuff comes from the fact that people are people. We've been going into space for 65 years now. We've launched about 7,000 spacecraft. There's about 3,500 maybe still in orbit. And of that 3,500, there's maybe only 1,000 that are still functional. And so this stuff comes from the fact that, people just drop stuff and don't clean up after themselves. And you'll see stuff on the side of the road when you're driving down the highway because it fell off of somebody's car or somebody accidentally dropped something and it's still there. And so all of the working in space is in that regard not that much different than working here on Earth. People drop things and they don't always bend over to pick it up and clean it up. So it's just one of the consequences of living and working in outer space. Explosions create space debris, batteries, propulsion units that are overly designed and overly fueled without any concern for passivation after the lifetime of the spacecraft. Those are basically stored energy sources just waiting to explode, and sometimes they do because materials deteriorate in space and wires come in contact, sparks happen, and things blow up. So it's just sometimes the designs are not that great. We had a wake-up call in 2009, in early 2009, where a functioning satellite, an Iridium satellite, one of the constellations that's up there, one of the earliest constellations that was up there, was hit by a defunct Cosmos booster. Nobody saw it coming, which is kind of scary. But the idea is not only did nobody see it coming, but nobody realized what a mess that would make. And so when the dust settled, literally, there were several thousand new sizable, which means fist size or larger, pieces of space debris fragments, which is huge, as we'll see. Now, this is not the only time satellites collided. There have been a number of explosions. There have been a number of collisions, even in the 60s and in the 70s. Some of them are accidental. Some of them are intentional. Every country has the right to decide what it wants to do for its future, and I'm all for self-governance, but it'd be nice if we could learn from the missteps of others, that sometimes sometimes the things that we are allowed to do, we shouldn't necessarily have to do them. And but the reality is that not everybody feels that way, and so people keep blowing things up in space, thinking that space is empty, which unfortunately space is not. There's a lot of stuff up there. There is stuff from all the way from micrometers, millimeters, centimeters, meter size. On the 10-meter size, that's like the size of a school bus. You have spent boosters. You have breakup fragments that are on the millimeter to centimeter side. You have meteoroids, naturally occurring debris, paint flecks. To bring it home to a little bit of a more popular level, stuff in this area here, faint flecks are about the size of a grain of sand. Breakup fragments are about marble size. MLI pieces and mission-related debris like wrenches and bolts and other toolkit drops. Now we have baseball in the U.S. I tried to get a picture of a cricket ball, but I couldn't find one. But I mean, I think they're about the same size. It's about like this big, right? So, that's what this is. But I did find something that I thought would be of interest to everybody to sort of bring it home, maybe to a local environment. A footy ball is about this big, right? It's somewhere about like this, right? I attended a footy game in Melbourne, and it was mind-numbing to see so many people run for so long without stopping over such a large area of grass. I was stunned by the endurance of those athletes. The game was fun. I had a good time. So anyway, footy ball is about this big, right? So that's kind of where we are as far as that's concerned. But anyway, just to give you some scale idea. How has the population grown? Well, exponentially is probably a good word. This is a picture in the 1960s, and you can see the changes happening over the years. Now, this is not to scale, because some of these dots are the size of Canberra, obviously. But you can see that in the 70s, there was created when we started sending stuff into geosync, there's a lot of stuff in the geosync orbit, and LEO pretty much now obstructs, in a sense. There's just so much stuff in LEO that you can actually imagine it being covering up the entire planet. And here's the exponential growth that I was talking about. When I started out in this program working on space debris, that was in the late 80s, right here. The rule of thumb was that there was about 8,000 pieces of stuff out there that NORAD kept track of. Now, NORAD, if you're familiar with NORAD, NORAD is the agency that keeps track of where all the space debris is. It also keeps track of where Santa is on Christmas Eve, but that's another story. But it monitors and keeps track of the objects in space wherever they are, and lets companies know when there might be a close approach. So yeah, in the 90s, when I was doing my basic research, it was right here, right around 8,000. There was an anti-satellite test in like around 2007, yeah. That made a jump from 8 to 12. Then there was the Iridium Cosmos collision here, jumped from 12 to 14 something, and it's gone down a little bit. There's been some natural decay and some things leaving, but it's starting to pick up again because more and more people are getting excited about space. So we're on the way up. This is if you are interested in a graphical representation of the growth of space debris. So what can happen? So that's where it is. That's how much is out there. What can happen if you interact with a piece of debris? Well, one of my favorite answers to a lot of questions I get from students is it depends, because it depends on where you get hit and by what you get hit. Okay, so if you get hit by something real small, by that sand grain, you might have a small hole or crater. If you get hit by a marble, well, you might lose a solar panel. Yeah. If you get hit by a cricket ball or a footy ball, that's going to be a bad day. That's just going to knock you out. All right. That's just not even going to go there. And of course, depending on if you get hit by something even bigger, you can knock out an entire system. But something like the space telescope or any telescope can also be destroyed by a piece of sand if you happen to hit the piece of sand right in the lens, right in the mirror. So again, how bad is an impact? How bad is it? Well, it depends on where you get hit and by what you get hit. Okay, so it could be disastrous. how do we know what happens when we get hit? How do we know what happens when we interact with the stuff that's up there? Well, for the last 3 decades or so, about every 10 years, we have been testing ground-based testing of mock-ups, satellite mock-ups. And then we have graduate students. So whoever's a graduate student out there, thank you for being a graduate student, because we rely on you for this kind of stuff. We count the pieces, we measure the pieces, we weigh the pieces, we do a length to diameter, a characteristic length, radar cross-section of all the pieces. And then we try to predict then that if you have a satellite that has these basic pieces on it, it might end up looking like this. And then we develop what are called standard breakup models. This was in the 1980s. In the 1990s, there was a NASA Japan satellite test where you can see that the pieces of the satellite that came out were a little bit different than the socket test, the previous test. There were about 5 tests, I think, in the 90s and 2000s. And so there are obviously some wires now, and there are obviously some square pieces and chunky pieces. So it's really hard to measure and figure out what exactly is going to happen to a satellite and how it's going to contribute to the debris environment. But we're now ramping up the fidelity of these tests to the point where the most recent test performed by NASA in cooperation with the University of Florida really had a really solid looking fake satellite, mock-up satellite. It had MLI, it had solar panels, it had radio antennas, it had all kinds of pieces of, it just looked like a real satellite. And so now we have hundreds of thousands of pieces lying on the floor that tens or dozens of graduate students have now moved through and have analyzed and have categorized and have written theses and dissertations about. So this has been a huge boon, a huge boost to our ability to be able to predict what a satellite is going to do when it gets hit by a piece of debris. So that's really cool. We can now then upgrade our environment models based on this new information. Now, I know I'm dealing with an AIAA section here, so you guys are supposed to be pretty smart, but I'm just going to give you advanced warning. There's math coming, okay? You're eating lunch now, I think, so hopefully you have not had too many carbohydrates. Hopefully you're not sleeping yet. Hopefully your brains are still working. But here we go. How fast is it? Why does a satellite fall apart like that? How could it possibly break up into so many thousands or hundreds of thousands of pieces? Well, if you do the math, and you can follow this along, look at the details later when the recording is put online. But basically, the math tells you that for an object in low Earth orbit, if it is coming straight at you, both of your ram directions are into each other, you can get hit at 16 kilometers a second. That's pretty fast. So if you remember your thermodynamics, because this energy gets dumped into the system so fast, it doesn't have time to dissipate. The material melts, vaporizes, pulverizes, and it just gets destroyed. Okay? So that's why this energy dump is so big that it creates such a disaster. Okay, and if you take a look at the if you take a look at a film stills from a fast film of an impact, you see this debris, this particle coming down here, hitting the thing, and then it hits. There's backsplash, and then there's this bubble. It basically looks like a teardrop. That's because things are melting, things are behaving as fluids. And then it hits the second wall. This is such an energetic impact that it has a tremendous effect on destroying whatever it hits. And that's why the satellite does that. We attempt to reach these speeds with using light gas guns, which can actually can get sizable projectiles up to 8 kilometers a second. So we can use it to simulate what happens at high velocity, but we can't really get to those really, really, really high velocities. So the question now comes up, well, how are our space assets doing? And they're doing pretty good. You know, space telescope's been up there for a long time. It gets hit all the time. The worst that we found was a 1/4-inch hole in one of the antennas. Space station gets hit all the time. It's not a question of when, it's a question of how often. This is a photo. You can't really see much here, impacts on the radiators. But if you do a close-up, you'll see dozens and dozens of dings and pings. This is all either meteoroids or pieces of space debris. Handrails, you know, astronauts do this crawl walk when they walk across the space station. Well, they came home with torn gloves, and nobody could figure out how are astronauts getting their gloves torn. Well, until somebody figured out that all this stuff, all these little pieces of debris are hitting the handrails, and as the astronauts slide their gloves across the handrails as they walk, they're tearing up their gloves. Who knew? Solar arrays hit all the time, damaged all the time. Nothing's been catastrophic. The lives have not been lost. There's been no real shutdown, but this kind of damage does happen. Space shuttle windows damaged all the time, had to be replaced. Well, I say all the time, had to be replaced frequently. Okay, it was just kind of one of those things. So human missions are very susceptible to space debris. And this is the scary part. The spacesuits that are up there now can be perforated by a millimeter particle. That means the size of a grain of sand can puncture a spacesuit. And that would be, for that astronaut, a really bad day. Okay. So then we got to think about how are we going to protect ourselves, and how we protect ourselves depends upon what we send up there. If we send up something like the International Space Station, which is human occupied, it's very heavily protected. A satellite in GEO, you know, $350 million satellite. Hey, what's $350 million between friends? You know, if it gets taken out by a piece of debris, we'll just have to build another one and put another one up there. Okay. So it depends on what you send, the amount of protection that you put it up there. And there are different kinds of protection that you can use. You can use passive protection, active, and operational. Those are the three basic categories of protection. You can imagine active protection. When I say active protection, I'm talking about, you know, basically blasting something. All right, that's active protection. Now, that actually sounds kind of silly. And if you've been paying attention, what happens when you blast something in outer space? You create more debris. That's right. So, but that's okay. Somebody actually went through the effort of figuring out how we can do this. So good for them. That's good. I'm glad to see that it hasn't been put up there yet. Maneuvers are basically the way that we deal with large pieces of debris. The blue dots here represent ISS orbit crossing objects, and these are all the collision avoidance. How many times the collision avoidance had to be done over these years? 2015 looks like there have been 4 or 5. 2021 looks like we are having right around 2 or so. So yeah, every now and again the space station's got to do something. Has to adjust its altitude, has to adjust its attitude. Active protection sounds great, but the sensor capability that we have just isn't that good yet. And so it's not a very popular way. It's not a very useful way for protecting ourselves. Operational space protection is pretty much the cheapest way of doing it. It's basically working smart in space. Don't fly with windows in the ram direction. Space shuttle hardly ever flew with windows in the ram direction. It usually flew with its SSMEs in the ram direction, because once the space shuttle was in orbit, the SSMEs did their job. We didn't need them anymore. Well, we'd like to use them again, but if they got ruined, that was okay. So we protected the vulnerable parts of the spacecraft by pointing it backwards, if you will. Passive protection, this is where I've done most of my work, is basically like the bumper on your car. You know, people say you don't need insurance until you need insurance. Well, you don't need a bumper until you need a bumper. You put it on your car, you hope you never have to use it, but if you have to use it, it's there. And it's basically there to protect the spacecraft by absorbing the initial impact and distributing the debris momentum over a larger surface as it moves towards the spacecraft itself. So we protect our space station by putting shielding, by putting bumpers all over it, especially in these red zones here. These are the red zones. These are the areas of the space station in the flight direction. And so we put a lot of shielding where the zones are red, not so much blue. We figure out where to put this by doing what's called a risk assessment, which involves taking a model of what it is that we want to protect, running it through the environment of the debris that it's likely to interact with, using failure criteria to predict what might happen, and then coming up with areas that need the most protection, which are the red areas here. And so this kind of iterative process has led to enhancements of the space station debris protection system. This area in this Russian module was identified as being very weak and very susceptible to damage from debris. And so these little gray panels are add-ons, add-on debris shields that were put there after the module was launched and after it was installed. And that results in an increased overall protection for the space station. Has this stuff ever fallen to Earth? Well, if you live in Australia, you know this stuff comes down sometimes right in the middle of your own backyard. The big stuff especially comes down all the time, and it's luckily never hit anybody yet, but it does come down, and so it is a problem. This is an image of the ATV satellite burning up as it comes in over the Pacific. Now, where is it going to land? How come we can't stop that from happening? Because quite frankly, we don't know where it's going to land. There's a huge amount of error involved in predicting how a satellite breaks up, what's going to happen to the pieces, what those pieces are going to look like, what the atmosphere is going to be like in 3 hours, in 3 days, in 24 hours, and where it's going to land. So we can predict general areas. It might come down somewhere in the Indian Ocean. Well, that's probably about as good as we're going to get. And so what the future is going to look like, well, that's up to you all. That's up to the new generation of scientists and engineers. We're working really hard to keep things under control. But with space launches increasing, with satellite launches increasing, it's going to be tricky business in the future, how to keep the debris population under control. One of the best things we can do is be smart about how we design spacecraft and to passivate our spacecraft after their usable lifetime is over. Deplete stored energy, jettison fuel, make sure batteries are not charged overly. Yeah, I understand that you don't know how much fuel or batteries you're going to need until you get there, but don't top off the tank too much. Nature doesn't really help us a lot, unfortunately. Yes, there is an 11-year solar cycle, but the amount of heating in the atmosphere does not go very high, and you need it to go a lot higher than it goes all on its own if you want to, rely on nature to clean it up. So that's no good. If it's going to get better, if it's going to get worse, if it's going to get worse so bad that it's going to get worse, you could have something called the Kessler syndrome, where you have a chain reaction of collisions. And you may have seen some movies about this, and this has been recently in the popular press, where you might have so much debris out there, they all collide and they all create this cloud around the planet that's impenetrable to sunlight. I mean, it's a scary scenario, but mathematically it is possible. Okay, so as we wind things down here, I'm gonna give you guys another quiz. All right. So you're in charge with reducing the debris population. You have two choices. You can either go out there and get lots of small debris particles, or you can go out there and get a few big pieces. You only have a limited budget. I don't know. Pretend you're rich, $100 million. What are you going to do? Are you going to go out there and get millions of smaller particles? Or are you going to go out there and maybe get a couple of dozen big boosters? So don't think about it too much. Probably formulated an answer in your mind. The answer is you want to get the big stuff, even if you could only get a few dozen. Just think of it this way. You spent $100 million, you've collected 10 million pieces, marble size and smaller. And a day and a half later, two big boosters collide and create several hundred thousand more smaller pieces. All the money and hard work that you did to collect the several hundred thousand small pieces is just out, is gone. It's just wasted. It's useless what you just did, because you just put in just the exact same amount of debris. The idea is, when you're out there to reduce the environment, you need to go after the big stuff. You have to reduce mass. That is what's going to do the most benefit if you're going to want to reduce the debris population in the future. And there are lots of great ideas out there. There's tethers and there's lasers that push it gently out of debris, and it'll then elliptically orbital and come back in. And there's all kinds of stuff out there. Finally, European Space Agency went out there and tested three means of bringing down big pieces of debris: net capture, harpoon capture, and attaching a drag sail to deorbit it. And I think they finally, I think last year, a couple years ago, they did the drag sail. That was the last one. There's lots of cool videos online. So if you're interested in that, I would suggest that you take a look at that and see if you can find some of that. But Remove Debris is the name of the project. European Space Agency. There's all kinds of cool stuff that you can see where it really works, and it's really good to see some of this technology being proven and coming to fruition. So then I just like to close it up, I guess, with the idea that it's really cool when you're standing looking at your kids. We have this thing called book fairs. I don't know if you all have that, where parents are solicited by their children to, please, mommy, please, daddy, can I have this book? I want to buy this book. It's a really cool book, and there's a book fair, and could you buy me some books and all that kind of stuff. My parents would never buy me those kinds of books, but that's okay. So I was looking through the books in the book fair, and I found the space station book. And okay, that's kind of cool. And there it was on page 40 in this kid's book on space. They're talking about space debris and Whipple shields. Wow, how cool is that? And I think ultimately that's what we got to do here. We got to teach our children, got to help each other to be mindful about what it is that we do in outer space. And space is a limited resource. Yeah, space is big, space is huge, space is not empty, especially where we go, where people go into outer space when they launch into outer space. So we have to be careful about that and to protect it for future generations. So that kind of gives you, I hope, a little bit of introduction into the wonderful world of space debris. And it's been fun. It's been 3 decades plus now, 35 years just about, that I've been working in this area. And I've learned a lot. It's like drinking from a fire hose sometimes, but it's been enjoyable, and I'd be happy to try to answer whatever questions you all may have. So thank you for your time, and thank you for your attention.
Thank you so much, Dr. Schoenberg. That was a great talk. Any questions? Please send them to, I've sent you a message in chat. Just send the questions in. Gennady already started. He's asking where the recordings are. Sorry, Gennady, the recordings are all on AIAA Facebook page. I'm just going to I will pass you the link in a minute. I'll just send you the link. The recordings are usually available 2 to 3 days after the talk, and they are all on AIAA Sydney section Facebook page. Anybody else? Any questions for Dr. Schoenberg?
Chat lines are firing up.
Well, it takes a few minutes for people to type, right? So Bill's asking which method of deorbiting is the most effective? Is it laser, or what is the easy way to deorbit?
Well, first of all, I have to stay in orbit long enough for you to see me. Wow, that's crazy. All right, I'm going to stop the video. Well, I think I'm going to stop the video because it shouldn't be doing that, right?
I think it's the background. If you stop the background.
Oh, that could very well be. Okay. I like people to see me. I like to see people. So the question is which preferred method of deorbiting, right?
Yeah, well, is most effective. Is it laser, such as laser? Bill, I assume that's when you don't have any more fuel left in your cells to propel you into the lower orbit.
Right. So what's the deorbiting is very tricky because you have to be careful not to deorbit the wrong thing. In fact, I gave a similar presentation to a group of lawyers who deal with space law. And it's actually very interesting. Just because I think your junk is in my way doesn't mean that I have the right to get rid of it. And so you can't always assume that just because there's a piece of junk up there that you have the right to move it out of the way. So it's actually, deorbiting things is a very tricky question. And so in terms of what's the most effective, I think they showed that the net is very good. I think the solar sail takes a little bit of time, but in both cases, you have to have a good aiming technology, and you have to be able to hit your target. Now the net's big enough so that you can imagine you're kind of like in those old movies where they're throwing a net at someone who's running away and that person stumbles and falls, right? I mean, that's basically what happens. Shooting at a harpoon at something, that kind of scares me a little bit because of what can happen if you miss, and also what can happen if you hit it and all the debris that you might create. Lasers are good, but yeah, I worry about that a little bit. I guess so. I kind of personally like the net approach.
Right. Naomi is asking, is there an inventory of a junk, and is there a requirement to list it and the location?
Is there an inventory? Well, there is. Yes, there is an inventory, and different countries have different tracking organizations that keep track of it. So it's not so much that. Well, okay, yes, there is an inventory of the really big stuff, like boosters and defunct satellites. You can actually find that. But the little stuff, the inventory is basically 2 lines of code where that they tell you what the orbit is and where it's going and how it's precessing and all that. So when you say inventory, it can mean different things to different people. But the really big stuff, yeah, there was a splashdown that occurred over the Caribbean. A couple of friends of mine there called me up and said, "Hey, do you know what this was?" So I contacted some of my buddies at NASA and said, "Do you know what this was?" And he said, "Let me take a look." And he backed it out, and he knew the kind of stuff that could possibly have come down there based on where he knew the big stuff was. So yeah, there is inventory. What is the second question? Second part?
Is there a requirement to list it?
Well, no. Nobody has to say anything about their stuff. That's one of the interesting things about law in outer space, is that we're still kind of in the formative stages here. You're supposed to list, dangerous ingredients in food, right? I mean, that's kind of like law in most countries, right? But no, you're not required by law to list. If your satellite died, you don't have to tell anybody about it, which is kind of interesting.
I have a question. Is when you deorbit large stuff, so we're talking, the Chinese space station that went down in Australia, that went down in the Pacific.
Right.
How easy or how hard it is to aim it properly, so it falls apart in the control manner, as opposed to just shattering randomly somewhere?
Very difficult. I hate to deal in absolutes, so I will try to never use the word never or impossible, because that's pretty absolute. That's pretty rigid there, right? So I would say very difficult. In fact, nearly impossible. You can maybe steer it and get it within a little bit of an orbit, plus or minus, but then once it deteriorates and starts spinning, all bets are off.
For large pieces of junk, I mean, this is like asking how long is a piece of string. For the large pieces of space junk, how is there a formula of how many pieces fall apart? Do you expect to fall apart? Like, is it 1/3 of the unit fall apart in orbit, creates and then creates debris,
Right.
while the rest falls? Is there a general formula for that?
There is not a general formula because, of course, every spacecraft is different, but there are general formulas that can predict. There are that's what the NASA standard breakup model does. For example, it says if I have a satellite of so and so mass and so volume, then chances are my pieces, when it gets impacted by a given amount of energy, are going to follow the following distribution. So there is some information that you have to dump, you have to provide into that formula, into that model, and bringing that model back down to Earth, if you will, is a little tricky.
Oh, great, thanks. So a couple more questions.
Sure.
Bill's asking, are there any companies or countries still launching satellites which do not have end-of-life plan?
Yes. There are, and very fewer and fewer. There's an international agency that promotes the cooperation and sharing of information as much as is possible and allowed by various laws within various countries. But everybody is encouraging everybody else to prepare. And, when you get to my age, to talk about things like end of life, it kind of makes you pause and kind of makes you pause for a minute. But yes, there are countries do require end of life plans, end of mission plans for their satellites. But countries, including the US, we are well known for granting waivers for those requirements, because sometimes it's just impossible to meet those requirements. And if we can provide a justification why NASA should waive that requirement for my company so I can launch this satellite for this reason, it goes through a review, and I'm sure every country is different, but in some cases, in some regards, every country is similar. They review the waiver requests, and then if they're granted, then they go up without any end of mission plans. That's not as frequent anymore, but it does still happen.
So to follow up on this question, actually Naomi asked it, is are there any laws in space regarding this, and is it going to become an international law, the end of life and junk removal?
Right now, there are no international laws that I know of that are specifically addressing junk removal for space debris. There are several laws that address the cleanliness of space, protecting space, things that you can hang a debris removal requirement on. But that phrase, it's only now starting to be discussed. So there's nothing that you can cite chapter or verse that says country X, upon launching after 25 years, shall not endeavor, but shall ensure that the satellite destroys itself or crashes somewhere in a harmless part of the Pacific Ocean. Blah, blah, blah. No, there was nothing like that.
All right. Well, we can squeeze one more question in if anybody has it. Then we will wrap up for today. Need to give people time to type.
Sure. And when you see the presentation on your Facebook site, my email address is on the first page. So feel free to send me a note if you'd like. I'll try to respond as quickly as I can. But anyway, go ahead. I'm sorry.
No, it's okay. We don't think we have any more questions. So I'll wrap up the session, stop recording. Thank you so